Okay, welcome back, everyone. Our next speaker is going to be Michał, who's come over from Poland. He's also the founder of Monadic Warsaw.
Yeah.
Never wrote to Yep. And he's going to be talking to us about recursion schemes. But before we jump into that, just a quick announcement. After this, we're going to go into the keynotes. That's going to be in almost exactly an hour. The keynotes are, sorry, not the keynotes, the lightning talks. Lightning talks are going to be run pretty much on every 15 minutes. There will be a bit of time to move around them. So if you do want to move rooms between the lightning talks, obviously feel free, but they will be starting every 15 minutes. But other than that, welcome.
Thank you. So in this talk, I know I haven't made it obvious from the title, but I'm going to talk about recursion schemes. And the idea here is to give a mortal level introduction into recursion schemes so that you actually understand what's going on in them and how they're used, not necessarily to present all of them, but maybe to present some underlying principles and the way that they function in programs. So the usual way we tend to write, is that visible? I'm not sure if, maybe I can actually do something about it. No, actually, it'll take 5 minutes. Yeah, exactly. Yeah, let's do that. So the usual way of writing recursion for data type that's recursive is like that. So say we have a very, very simple AST, which can encode integers and their addition and multiplication. So we have the constants, which are the base integers, and then we can add them and multiply them, and we can write an AST with a couple of additions and multiplications. And then if we want to pre-print it, we just write a function like that, where for the integer we print it, for the plus sign we print it, and same for the multiplication. And it's all well and fine, but we are writing the recursion ourselves here. We're actually controlling what's happening here. We can make a mistake, or people may not understand what we're doing here, in more complex cases at least. So can we do better? Well, we can introduce a slightly more complex recursive type, where instead of having the expression in here, we have a general thing. What that thing will be, we'll see in a second. And we can, so you can see that that's basically the same thing as here. It's just that instead of the expressions, this is the general place. And that data type is also a functor. We can have GHC derive that for us, but we can also do it for ourselves here, so that we are certain this is a functor and we understand why next slides look like they look. So in order to have a functor, we have to define the fmap function. So we have to have a function that transforms an element into another element, and then given a functor, we get a functor with the other type. So how may we write that functor for the expression f? Well, for the constant element, we just return the constant element. And then for the addition and for the multiplication, we do the same thing, which is apply the function, the mapping function, inside the addition and multiplication constructors to both elements. So why don't we apply the function in for the constant element? Well, that is because we have a general, we have the int here, right? So had we applied the function that brings that to b, that would no longer be an int, so we can't make it more general than it is in the type. So let's check if this is indeed a functor. We need, one thing is the fmap function, which we have, but then the fmap function needs to abide by the functor laws. So one functor law is that the fmap of the identity is identity, And then the other is that f-map of the composition is the composition of f-maps. So there is nothing really to prove in the identity case. If f is identity, then we get, well, first line is the same. Here we get add of A, which is the same without the f-map, and same for multiplication since it's the same structure. And then for the second part, we do it for the addition case because multiplication is the same. So the addition of the composition is the f-map. We take out the f, which we can do just looking to the left on this operation. And then we do that again, and we arrive at the right side. So this abides by the functor laws. So this is a functor, which again we can get just by deriving functor. But yeah. So let's go back to our recursive type and think about how we can describe our AST with that recursive type. Well, we can have the constant element, but the type of the constant element is going to be an expression f of a. And then say we want to have an addition, but then the type of the addition of two constant elements is going to be an expression f of a. So we want to do something with that type, right? We want to apply some operations to that type in order to do some recursion on it. But the obvious problem is that this has a different type than this. So it seems that the only thing that we can do here is to use template Haskell and generate an arbitrarily nested instances of our functions for each of the things in here, but we don't really want to be doing that. So let's see what we can actually figure out to not do that. In order to not do that, we will use the fixed point of a functor, which is an infinitely recursive data structure. So in here, so those two definitions are the same. The second one just has the axis or to the inner part. So in here, for a given functor, this wraps a functor and then applies the same thing inside the functor. So this structure is infinite. And if we unwrap one level from it, so if we expand that thing that's inside, we take this definition from here. This is also a fixed point, and we can expand and expand and expand and expand. And same for wrapping. It's always the same fixed point. So how do we use it? Well, let's take our previous thing, which is we add, well, and we also add a multiplication. So we have two constants, we add them, and then we multiply the result. So we can wrap the innermost part inside the fixed point, check the type, and the type is the fixed point of expression f. So the functor here is our expression f. And then we can wrap it again, and wrap it again, and wrap it again, and wrap it again, and check the type, and the type is exactly the same. So even though this looks more complex, the type is the same. So if we can get the function that can operate on this type, we can actually apply some operations to it. So what function would operate on that type? Well, the whole idea of recursion schemes is that we can separate the walking of the tree, so the actual recursion, from the function that operates on an individual element. So the function that would operate on our element is, again, the pretty printer, but here there is no recursion, right? So for the constant element, we show it. For the addition, we just take the two elements and we concatenate the string, and for the multiplication, we concatenate the string again. So we have the pretty printer, but it operates on strings. So that's weird, right? We achieved that and we can use it with the catamorphism. So catamorphism is a generalized fold, basically, that if we apply to our our AST, we get the string representation. So, so how does it work? Like how, it seems a bit magical, right? So it just, we give it the function and it gives us the output. We don't specify the recursion at all. So let's see what it does. It first gets the expression and it removes one level of the fixed point. So we get the expression that starts from multiplication. Then we fmap on that. Fmap on that goes level down with the function, and it applies the catamorphism again, so it removes one level of the fixed point. Then we fmap on that, so we go to the innermost element, but then the fmap of const is, as previously, is just the const element. So we pass the const element to our function, which is print_alc in that case, so we get a string. And then we do the same here, and then the f at the level of addition gets two strings, because those are, one string comes from here and the other one comes from here. So it operates on the strings. And so all the time, and we wrap up into a single string, and we end up with a string at the end. And the type that's here, so the type that we end up with here, it's called a carrier type, and it can be anything we want. Doesn't have to be a string. It can be in any general function. So we can also write a function that figures out the numerical value of this. So we use the same catamorphism, and we use the getValue, and we get the numerical value, which is pretty nice. So we have the same way of walking through the AST. We can test that. We can make sure it's correct. And then the only thing where we can make a bug is actually what happens to each of the elements, which is the same as we can get the same behavior with fold. It's a simple isomorphism. So is there a way to get unfolds? Where? Yes. So instead, so the previous operation that was the FA2A was called in algebra. So we can get in dual of that, which is a coalgebra. So we get a seed, and from that we get our functor. So let's write an operation like that. So say if we get small i's, then we create an addition, and then if the I is bigger, we just put the constant element in there. And so this was easy, and we have the arrow effectively reversed here. So let's try being naive and just taking our catamorphism and just reversing the arrows. So putting f at the beginning, and then instead of taking stuff out of the fixed point, we put it in the fixed point. Will that work? Yes. So we can just do the anamorphism unwrap of 1. And this works, but there's no way to actually print the fixed point to the terminal. So we can use our previously defined pretty printer, apply to that, and we get our AST pretty printed into the terminal. So again, how does this work? Well, it applies applies our passed-in function to 1, creates 2 addition nodes, then f maps into those, applies functions, so on and so forth, until we get to the constant nodes in here, and then we wrap each of the levels inside the fixed point to get a fix, so that the types match. So we get each of the levels wrapped in a fixed point. The same way we had it in here. So each of the levels is wrapped, so we can recurse inside. In some cases, we need access. Not only we need access to the current value that's being printed. We also want access to the original elements. So in our catamorphism, we operated on strings. So if we wanted to see what that value, what that value that we get in the addition operator is, we would have to parse the int and then do something with that. But that's error prone and that's silly. We can have access to the original underlying value that the addition operator gets as well. Especially that in some cases parsing is not only ineffective, it's just it may be ambiguous as to what the original value is depending on our pretty printer or our function that wraps it up. So paramorphism is very similar to our catamorphism. So we unwrap a level, do a thing at each level, and then apply our function. The only difference in here is that the thing is a combination of two parts. So one is our original, what catamorphism did. So we fmap and apply it one level deeper, but we also keep around the original value that wasn't transformed. An example of dealing with that would be this slightly silly case where for the additions we want to sum up the numbers, but for the multiplications we want to keep them as a string. So we have a minifying pretty printer of sorts. So again, the const is the same. For the additions, we take the original value for both branches, and then we apply a catamorphism to sum it up. So we sum up both branches into numerical values, and we add those. And then for the multiplication, we discard the original value. We just care about the pretty printed value, and we pretty print it, and it works.
Can we write para as kata?
Yes.
Because I mean, para looks like your kata function, so I wondered if you could write para in terms of kata.
Yes.
Yeah. Okay.
Something with the microphone.
Sorry.
That looks like something you might use to like run optimization passes over an AST or something. Is that would that be an application?
That could be the case. I mean, the uses depends on the users, right?
Yeah.
But yes, this could be used for that. Anything you desire, to be honest. So I really like this example. The example comes from Jared Tobin. If he's here, then kudos to him. It shows really nicely how how if you have a data type that represents your problem really well, you can have a clear and concise solution to that problem in like a couple of lines of code that is also quite beautiful, I think. And it also touches recursion schemes, the ones that we've just learned. So say we have a square, and that square have dimensions of the power of 2, so we can use a quad tree to represent that square. So for those that don't know, the quad tree is a tree that has 4 leaves. I mean 4 nodes underneath each of the nodes. So in here we can take our 4x4, divide it on 4 elements, and then each of the 4 elements will have a leaf with 1 character inside. And now the problem is we have the square in here, we want to rotate it 90 degrees. That might not be so obvious here because the font isn't square, so it looks like a rectangle, but it is a square, you can count. So let's define our quad tree. The quad tree will have a node with 4 elements, a leaf with a value of an arbitrary type, and then the empty element in case there's no value at the given point. And we can also And that's our quad-tree functor, right? So we need that to be functor in order to apply the fixed point to it. So our quad-tree helper type will have the fixed point applied. So if we create the quad-tree on each level, it will be wrapped in the fixed point, so we can, again, recurse into it. And we can define a couple of helper functions, which aren't really, in order to create a node, we wrap it into a fixed point and we create a node. And same for the leaf and same for the empty element, we wrap it inside the fixed point. So let's take our initial quad tree and define it in such a way that it's the top left, then top right, then bottom right, and bottom left. So the top left quadrant will be false, true, false, false, and then we have false, 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 true. So we go like that, right? And we go in the same direction in those quadrants. And then let's define the catamorphism that rotates the whole thing. So in order to rotate, we just permute that thing to the right. So this lands at the beginning and all of the elements. So we move one to the right. And if we pass that tree into the rotate, we get a rotated tree that's rotated 90 degrees. So it works, and the whole algorithm is in here in this permutation, and it applies that recursively on each level, so we get the correct rotation. So let me show you, that's the part when I attempt to do a live thing. Let me show you. Oh, my terminal had died. So there we go. Can you see the text, or do you want it bigger? I don't know how large it is. Okay, so the thing that I've presented uses catamorphisms that are defined by me, right? So those are very effective catamorphisms, and this is the way that they're defined, and this is the way it works. But in real life, we probably won't be using our own definitions. We'll be using a library of sorts, right? And the standard library for recursion schemes is called recursion schemes, and is written by Edward Kmet, of course. And you can get it from HaskellX. And it's way more general than our mortal level recursion schemes here. So it uses type families so that you can use the same kind of morphism for different types. But the only thing we'll be interested in here is the fixed point case. For the others, either the recursion is way more complex, or, it would require a 2-hour talk to get into some of the concepts in here, so I won't do that. So we have the catamorphism, and in here, if we, let me just comment it out for a second. So if we substitute the instance of the base class for the fixed point, what we get, so the base for the fixed point, f, is just f. So in this case, we get the kata is f, fa, to a, fix f, to a. So this bit is our algebra, as we had in our catamorphism, and we pass it our AST, wrapped in the fixed point, and we get the answer. So this is exactly the same type that we had on the slides, and you can check that if you use the catamorphism from the library and you passed it the getValue function, you would get the same answer. So those functions are completely plug and play. One really cool thing that we can use the library for is Fibonacci numbers. So using a catamorphism for computing a Fibonacci number would get pretty intense very quickly, because we don't have access to other levels, right? So we would need to keep some kind of a state around, and then we wouldn't really have recursion schemes anymore. Otherwise, the complexity of Fibonacci, the naive Fibonacci computation is 2 to the power of n, so we would run out of computing power very quickly. But we can use a histomorphism, which is again very similar to our catamorphism, but it also keeps all of the previous computations around, so we can check what was the value a certain number of layers deep. The structure that enables us to do that is the co-free co-monad. For those that haven't actually encountered infix constructors, this is just, the sat phase is just a constructor name, so you could have it written like that, but it's just a convention. So the left is our value, so that's what the catamorphism has, and the right is the wrapped set of previous values that we got. And we need a functor to operate on, to make a fixed point of, and we need a Fibonacci number at a certain index, and in order to get a functor that corresponds to a certain index, we'll use piano numbers. I'm not sure if that's the correct pronunciation. But basically, we'll encode the natural numbers as a sequence of constructors. So 3 would be isomorphic to next of next of next of 0. It's not equal, but that's how we would represent 3, and so on and so forth. We can write an expand function that helps us in achieving that. So we get expand of 3 will give us that, and also wrap each of the levels inside a fixed point. That's that function. It's fairly straightforward. We terminate at 0. And then for the meat of our Fibonacci function, so for the 0 case, we output 0. For the 1, we output 1. So if the previous element had outputted 0, I mean the parameter to the previous element was 0, then we know we're the first element, so we output 1. And for each of the next elements, we get the value of the previous element, and we get the value of 2 elements back. How do we get the value of the previous element? Well, we take our cache, and we take what's on the left, which is what the previous element had returned. So the right is what the previous element was given. So we get that value, and we return it, and then for 2 levels down, we unwrap it again, and we then go from this line up here, and we unwrap it again, and we get the value of 2 elements down. And to prove that it works, it's exact. Yay! So it can't be, the complexity can't be 2 to the n, because we wouldn't have gotten the number. So it seems to be working, it seems to be caching. And again, we didn't have to define the recursion ourselves. So recursion is handled by the histomorphism, which, as the name suggests, can hold the history inside. And the only thing that we have to define is what do we do at each of the steps of the recursion, and we have the property that we can look up the results and the parameters that were passed in the previous steps of the recursion. at any point that we want. And there is a huge deal of functions here that do many different things. So there is G chronomorphism, and there's probably a function for everything, to be honest, in case you wanted to. So to sum up, for some cases it might be clearer to use a recursion scheme to encode your recursion, like that summing pretty printer, I'd say. It's way clearer to define it as a recursion scheme because you just say what happens to each of the elements. It's not the case every time. For some operations, you might just, by adding a recursion scheme, you might just make the code completely unreadable to normal people who aren't familiar with that specific recursion scheme of yours. And sometimes code written with recursion schemes is faster than code written in the standard naive recursion. The reason for that is that GHC is supposedly better at optimizing a non-recursive code than it is at optimizing recursive code. So if you have a lot of meaty operations inside your non-recursive part, so inside the thing that walks the tree, it might be optimized better, and then you can get better performance. However, I've run some benchmarks, and the results are very close. There's maybe 5% difference for some slightly degenerate cases, but they're very close, so I don't think you should actually, unless your case is very, very special, you shouldn't, this shouldn't weigh in on whether you use a recursion scheme or not. There is one really nice connection between the fixed point and the free monad. So the fixed point is basically that part of the free monad. So the way that the free monad augments the free monad augments the fixed point is that it adds the termination part. So the case where you can terminate even when the underlying data type doesn't. So in case you were wondering how to use the free monads or how you operate on them, I think the recursion schemes are a really good intro into understanding those. So do you have any questions?
It's more of a comment than a question, and
yeah.
Thank you for the talk, by the way. Just going back to what you said about the free, you have a sum type between your fixed structure and your possible termination value, as you called it. It's probably worth pointing out as well, the co-free is a product type of your fixed point and a termination value,
yeah.
and that's literally the symmetry between the two.
It's a really good comment. Also, the co-free that was used in the histomorphism is exactly the co-free comonad. So it all binds together really nicely.
How long did it take you to wrap your head around recursion schemes? Because I'm starting right now, and my head feels kind of dizzy.
So my aim for this, the reason why I also didn't go very deep inside the real library, is that my aim was to give you some kind of a gut feel as to how it works, because I think that's the hardest thing. It took me a while, especially given that I started by reading papers, and they're very dense. But I think once you understand the catamorphism, then everything, well, okay, you can't see it, obviously. Then once you understand what the catamorphism is doing and how it walks to the bottom of your AST and then creates things from those bottom values to arrive at the ending value, then it all becomes easier. Because it's slightly counterintuitive. You think of recursion as starting at the top and then descending to the leaves. but your function is actually applied from the bottom up in this case. It is the catamorphism that walks down, and then your function actually gets the values from the bottom up. So that's people aren't used to that, I guess.
I have a quick question. Do you tend to kind of always start with this like expr f type thing when you're working with recursive structures, or do you tend to start with the expr type that you started with originally and then move to this and add recursion schemes kind of later?
You tend to start with.
Because it seems like it's quite a bit of kind of rewriting if you want to move from a normal implicit recursion to a recursion scheme form like this.
Yes. As far as I understand, yes, unless there's something in the commands magic types that does that for you. But no, you have to, in this case, you have to replace each of the recursion sites with a general type. And then you get a functor for free. So you could say it's a lot, but then is it? I mean, depends how many functions you have that operate on that, right?
I think it depends on if you've already written like a large amount of code already using the existing
Yeah, it's
type.
not a plug and play, no,
Right,
in
yeah.
no sense.
Okay.
Once you have the recursive type, it's fairly easy to add another recursion scheme because you already have the type and you know how to operate on that. But it's not trivial to move from a non-recursive to recursive.
Right. I'm not sure how much sense this makes, but you did say that you're recursing from the bottom to the top.
Yeah.
Are there recursion schemes to go the other way around? Does the question make sense?
It does. So an unfold, for instance, it goes the other way around, right? So so it's called anamorphism. So at first, so this one unwraps and then applies your function at the end. This one applies your function at the beginning, and then wraps. So this, in a sense, goes from the bottom. But I don't think there is a recursion scheme that applies your function while folding at the top.
Exactly.
Because then you would get explicit recursion, and
Yeah.
you wouldn't need the recursion scheme.
Thanks.
Okay, if there's no more questions, let's thank the speaker again.